Okay, thank you everybody. So we start again on this session. So it's a pleasure for me to introduce Hani from the University of Michigan, and he will talk about the mathematical theory of wave turbulence.
Okay. First, I would like to start by thanking the organizers for this invitation. I'm very happy to see some friends again, and it's an honor to be here at this beautiful place. Everything I will talk about today is joint work with UDenk from the University of Southern California. And the topic is on the mathematical theory of wave turbulence. So to start by motivating the subject, what we'll be discussing today falls under the umbrella of what's called Hilbert's sixth problem, which many of you are familiar with, I presume. So Hilbert's sixth problem asks for an axiomatic derivation of some laws of physics starting from first principles. So basically what you do is you take first principles, which are typically principles of dynamics, Hamilton's equation, as axioms. You don't question those things. And then you try to derive more elaborate laws of physics in a mathematically rigorous way. Okay?
The sixth problem is remarkable for its vagueness. It's very vague.
Yes, exactly.
It's not clear what it really is.
Oh, I will take advantage of this vagueness, yes. So yes, the main example is deriving the laws of statistical physics, starting from the laws of mechanics. Okay, so as you all know, statistical physics governs macroscopic quantities, like the first talk referred to such things, or like what's called slow variables in the previous talk, things like temperature, pressure, and its laws are typically time irreversible, the laws of statistical mechanics. So here you think of the second law of thermodynamics. There's a direction of time and along which entropy increases. Okay. In comparison, the laws of dynamics, which you can take them to be classical or quantum, these govern microscopic quantities like trajectories and orbits, and their characteristic feature is that these laws are reversible in time. There is no preferred direction of time there in Hamilton's equation or Newton's laws. So you get a sort of an apparent paradox, which was known for a while, because of this passage from something that is your first principle being reversible in time and getting out of it a conclusion that is irreversible. And this is what creates what is called the arrow of time over here. So this apparent paradox is adequately explained by giving a rigorous derivation, of the laws of statistics from the laws of mechanics. And this is the essence of Hilbert's sixth problem. So today, again, I will take advantage of the vagueness of this problem, and I will put it in the context of nonlinear waves. Okay? But before I go and start discussing Hilbert's sixth problem for nonlinear waves, let me give you the first or a typical example where this problem is set, which is Boltzmann's kinetic theory, or the particle interaction. So the kinetic theory of particle interaction. So the setting here is that you start with a box, for example, of interacting particles that are interacting via elastic collisions. You think of that there are n particles, and each of those particles has radius r, which is asymptotically vanishing. Okay, and those particles are undergoing elastic collisions. Okay, so we all know how the laws of elastic collision. You have conservation of momentum, conservation of energy before and after the collision. So you assume that the states of the particles are random at time t equals 0. The state of the particles, you take them to be random and independent. What this means that you can think of each particle having an initial density f naught. So this is the probability f naught of x. V is the probability of finding a particle at position x and moving at velocity v. And the key quantity that you'd like to find the effective dynamics is the so-called one particle density functional. And Boltzmann's ingenious contribution is that he found an effective equation of this one particle density function, which is given by the celebrated Boltzmann equation, which looks as follows. So you have a transport term on the left-hand side, and then there's a collision kernel on the right-hand side, Q of FF. What I'd like to point out for this collision kernel is that here you can write this collision kernel in the following form. in which you integrate over the velocities of the particle, ingoing and outgoing velocities of the particles. So I don't know if this is too small, maybe. So this integral is over v plus v star is equal to v prime plus v star prime. So v plus v star are the incoming velocities of the two particles, v and v star. And then v star prime and v prime are the outgoing velocities of those particles. And of course, you're integrating over v plus v star is equal to v prime plus v star prime. This is the conservation of momentum. And you're also integrating over v squared plus v star squared is equal to v prime squared plus v star prime squared. This is conservation of energy. Okay, so all those are natural, that this should appear in your collision kernel. And then you have those loss and gain terms that I won't elaborate on much.
These stars are in the well space of something, or is just a collection of notation?
So you're asking if V and V star are in
the tangent bundle of the tangent?
Well, here I'm taking a very simple, typically they should be, but here I'm taking a very simple situation where I'm working in RD, so V and V star are just velocities in RD. Okay, yeah. Okay, so and then the question is to Hilbert's sixth problem asks you to give a rigorous derivation of this Boltzmann equation starting from Newtonian mechanics that govern the particle collisions. And this was an open problem, and in many aspects of it is still an open problem. And it was a big challenge. The first...
it's still, right? I mean, nothing's proved, except, of course, the works you cite, but the actual question is still completely open.
In many ways, in many ways. So I will tell you what is known, and then I will also tell you the drawbacks or what is left for us to be known, for us to know, indeed. But in many ways, I agree with you. So the first contribution was by Lanford. This was the seminal contribution by Lanford in 1975, which was needed. This proof needed to be revisited and completed by many teams, including the ones that appear over here. So what does Lanford's theorem say? Lanford's theorem tells you that in the limit as the number of particles goes to infinity and the radius of the particles goes to 0, and except that they don't go to infinity and 0 arbitrarily, they go to infinity in such a way such that n times r to the d minus 1 stays bounded, stays an element to be order of 1. This is called the collision rate, this gamma over here, collision rate. So the condition is that they go to infinity in such a way such that gamma remains order of 1. Then you get two things. The first one is propagation of chaos. This was a conjecture, or this was an assumption that was made by Boltzmann to derive those equations. This is the conjecture of molecular chaos. But you can prove it rigorously in the following sense, that which tells you that you're starting with particles that are initially independent. Once you, this at time t equals to 0, once you turn on the nonlinear dynamics, of course, this independence is completely destroyed. But what the propagation of chaos part of this theorem tells you is that in the kinetic limit, if you take n goes to infinity and r goes to 0, this independence is retained. Okay, so this is a very deep statement, much deeper than one first appreciates on when you first read it. Because chaos is not propagated at the microscopic level. It is propagated at the macroscopic level. The second part is exactly the derivation of Boltzmann's equation, which tells you that the effective dynamics of the one particle density functional, which again you can think of it as the probability of finding a particle at time t moving at position x and moving at velocity v, this is something that is precisely approximated by the solution of Boltzmann's equation. Now, so this approximation is that the one particle density function is approximated by the solution of Boltzmann equation. This holds in the kinetic limit, n goes to infinity, r goes to 0, but only over times. Has only been shown that it holds over times that are order of gamma inverse. So these are short, rather unsatisfactory times. Maybe this is what you were referring to. We still don't know what happens for longer times. And this kinetic framework has been very informative, highly informative, and was extended to many other particle systems, not necessarily just those that are undergoing elastic collisions. So, and in some cases you get different kinetic equation, like Vlasov's equation, Landau equation, and etc. So today we will be asking this question. We'll try to do the same thing, but in the context of wave systems. So naturally, at the beginning of the past century, there was this sort of big question or big theme in physics of the duality of particles and waves. So soon after this particle theory had emerged, a parallel theory of statistical mechanics for nonlinear waves was written down. The first person to attempt that, as far as we know, is Peierls in 1929. But also Hasselmann in the 1960s in the context of water waves. And then this became a school by itself by Zakharov, Newell, and many, many others. So this list is highly non-exhaustive. So here, instead of the microscopic dynamics being given by Newton's equations, the microscopic themselves are given by a PDE, by typically a Hamiltonian PDE. So this Hamiltonian PDE tells you, so instead of thinking of a large number of particles that are colliding with each other, you think of a large number of waves that are interacting with each other. And those waves interact with each other according to your Hamiltonian PDE. Your PDE tells you how those waves collide, if you like. And instead of thinking of a large number of waves, we think of those large number of waves to be Fourier modes of a PDE. And this PDE is posed on a large box of size L. And we will think of the limit as L goes to infinity, which will replace the limit N goes to infinity in Boltzmann's particle theory. Okay. So today, our microscopic system, or our Hamiltonian system, will be given by the following PDE. So this is the nonlinear Schrodinger equation, which hopefully, well, maybe many of you have seen before. So there's a linear part, which is the linear Schrodinger equation, but then you have a nonlinearity, v squared v. So this is a cubic nonlinearity. And I put in front of the nonlinearity a parameter alpha, which corresponds in many ways to the epsilon parameter in the first talk. Okay, so we're thinking of alpha being a small parameter which stands for the strength of the nonlinearity, or the strength of the interaction. And then we are posing this equation on a box of size L, so periodic box of size L. So this will be a torus of size L. And this will replace, as I said, the number of particles. So L will go to infinity, alpha will go to 0, and alpha will be the analog of the radius of the particles in Boltzmann's theory. Okay, so all right, we can skip. All right, and then here's so here's the again another link to the first talk today. So we're starting with random initial data. So we're just like in the many particle case, and just like in the first talk today, we start with the random distribution of initial data. So how do we take this random distribution? We expand the initial data, which I call U initial. So this is the initial data of the nonlinear Schrodinger equation. I expand it in Fourier modes like this. Okay, so U hat of k is the Fourier transform of U initial at k. Now notice that U initial belongs to a box of size L, so the Fourier transform belongs on a lattice of spacing L inverse, okay? Because the dual of the box of size L is a lattice of spacing L inverse. Now, the key point is that how I take the Fourier modes. Okay, so I take the Fourier modes as follows. So let me start from the right and go to the left. So here, eta k of omega are IID random variables that have mean 0 and variance 1. Okay, think of them as Gaussian on a first reading, but they don't have to be Gaussian. And then I multiply that by the square root of n initial. So n initial, I take it to be a non-negative Schwartz function on RD. Again, Schwartz doesn't need to be Schwartz, but let's not worry about that for now. And so n initial will stand for the square of the Fourier modes, or the modules of the Fourier modes. So just again to link to the first lecture, what is really happening here from the physical point of view is that eta k represents a randomization of the phases. The phases are the fast variable in this theory. Okay, the phases of the Fourier modes are moving. They are the fast variable. Their time scale is order of 1. So there are actually 3 time scales in this theory. There is, if you look at the Schrodinger equation, you neglect the nonlinearity. Then the phases, you get basically a dynamical system for the phases, which you can write it in terms of the phases, action and angles. There's an action angle variables here, and the phases have a time scale order of 1. Now, if I add a nonlinearity like this, then there's another time scale, which is a 1 over epsilon time scale. This is the time scale where the nonlinearity starts showing up. Okay? And then on the next slide, we will see another time scale, which is 1 over alpha squared, or 1 over epsilon squared if you call this alpha epsilon, which will be the kinetic time scale or the Van Hoff time scale. Okay? But basically, what we're doing here is that the phases are moving so fast that we assume that initially they are random. Okay, that's what's happened. This is called the random phase assumption in the physics literature. Okay, so we call this this kind of initial data. We call it well prepared, because if I look at the expectation of the modulus of this initial data, then this is given exactly by n initial of k, and n initial will be the initial data for the kinetic equation in a few slides. So that's why I want to have this, that at time t equals 0, the expectation of the moduli of the Fourier modes is given exactly by the initial data of the kinetic equation. So the goal of the kinetic theory is just like in any kinetic theory, is to understand the distribution of the Fourier modes at later times in the limit when the size of the box goes to infinity and the strength of the nonlinearity goes to 0. Okay? So, and these are exactly the analogs of the limits in Boltzmann theory. A particularly central quantity is the modulus of the Fourier modes. This is the slow variable, if you can think of it this way. This is the slow variable for which you can try to write down an effective equation. Yes?
You said large L and small alpha, in which order, if it is relevant?
It is actually, so the order of L and alpha is very relevant, and we'll get to that. We'll get to that. Okay, so let's, so here's the conjecture, okay? So it tells you that in the limit as L goes to infinity and alpha goes to 0, so this is the large box limit and the weak nonlinearity limit, we have the following three things happening. Again, we have a propagation of chaos. I'm starting with initial data so that different Fourier modes are independent of each other. Of course, when I turn the nonlinear interaction, these start interacting with each other and they develop correlations. So this chaos at time t equals 0 is completely destroyed at the macroscopic level. But the key point is that at the macroscopic level, which means that in the kinetic limit, those different Fourier modes will retain their independence. Again, this is far from being a trivial statement. The second part of the conjecture is that there is a kinetic equation analogous to Boltzmann's kinetic equation, which tells you the effective dynamics of the amplitudes, the expectation of the amplitudes at later times. So, and these happen, this effective dynamics appears at a kinetic time scale, which is 1 over alpha squared. This is called Van Hoff time scale. So, as I said, there are now 3 time scales. There's a fast time scale, which is 1. This is the time scale for the angles. These are the fast variables. Then there's a time scale 1 over alpha, which is the nonlinear time scale from a deterministic point of view. And then I have here, there's a kinetic time scale, which is 1 over alpha squared that appears because of the randomization. Okay, so what does, more precisely, what do we expect? We expect to have that the variance of the Fourier modes of NLS at later times is well approximated by the solution of the wave kinetic equation, rescaled appropriately. So at time t over t kinetic, plus an error that goes to 0 in the kinetic limit, in the limit as L goes to infinity and alpha goes to 0. Okay? And here, this n of tc is the solution of the wave kinetic equation, which I will write for you on the next slide. Okay? And u of t is the solution of NLS. So this is really, for the rest of this talk, this is the equality that we will be mostly interested in achieving. Okay? This type of approximation between the solution of NLS and the solution of the wave kinetic equation at later times. Okay, and finally, there's a third part of this conjecture, is that it's not only you can find the variance of the Fourier modes, you can also get quite good information about the distribution of the Fourier modes at later times. You can get information about higher moments. You can get information also about the distribution of the Fourier modes at later times. Okay, so I still owe you the statement of this, what is this wave kinetic equation? It looks as follows. So this is the homogeneous version of the wave kinetic equation. So you don't see a transport term on the left-hand side of this equation, but you can consider an yeah.
So you said that 1 over alpha is the nonlinear time scale.
Yes.
But why the nonlinearity of the MLS is cubic? So it's not alpha minus 2?
Yes, it is. Okay, so it depends what you put in front of here. So usually, if you put, so strictly speaking, if I wanted to use dynamical notation, this alpha is epsilon squared. Okay, so if you start with the NLS without an alpha in front of the nonlinearity, and you think of the initial data as half size epsilon, okay, then this alpha would be epsilon squared. Okay, so the nonlinear timescale is 1 over epsilon squared. The kinetic timescale is 1 over epsilon to the 4. Okay? Yeah. All right, so this is, so you have a left-hand side, which is dTn, and the right-hand side, you have a collision kernel. Now, the collision kernel, as opposed to Boltzmann, is cubic in this setting. So it's k and n, and it's written over here for you. So there's a coincidence here, because I'm dealing with cubic NLS. The measure that I integrate over is the same as the measure that you integrate over for Boltzmann. So you integrate over xc1 plus xc3 is equal to xc2 plus xc. So this sign doesn't look like an equal, but this is an equal sign. This is xc1 minus xc2 plus xc3 is equal to xc. Okay, and then you're integrating over also xc1 squared plus xc3 squared is equal to xc2 squared plus xc squared. Okay. And then you have the collision kernel over here. So this is a wave analog of Boltzmann's equation. Again, this is a kinetic approximation that features a passage from something that is time reversible, which is the NLS equation, which is a Hamiltonian PDE, into something that is time irreversible, which is this kinetic equation. By the way, this kinetic equation, it is time irreversible because it does have an entropy that increases in time. So you can write down an entropy that increases in time. So you have this passage from, you have created this arrow of time that needs to be justified. And as I said, there's an inhomogeneous version of this equation, but let me, today we'll restrict ourselves to the homogeneous setting, which is written over here. Okay? All right, so we start with some history in the physics literature. So as we said, this arises in the 1920s in the physics literature, starting with the work of Peierls, but then it was generalized to, so Peierls wrote it down for in the case of nonlinear crystals, and then this was generalized sometimes independently to many other physical contexts whenever you have interacting waves, essentially. So then there was known work of Hasselmann in the context of water waves. And then in plasma theory, this was also developed independently as well. And then there came the school of Zakharov, Neuer, and many others who made this into a sort of a field by itself in the physics literature. And it is indeed highly informative in applications. It is used on a daily basis in oceanography and in optics and crystal thermodynamics and plasma theory. One important feature of this kinetic theory is that it gives you a framework for turbulence for nonlinear waves, and this is why this theory is sometimes called wave turbulence theory. Okay, this is beyond what I will talk about today, but so I'll just tell you a couple sentences about this. So the reason why it tells you something about turbulence is that as stationary solutions of this kinetic equation, there are some comes out some power law solutions. So these power law spectra appear as stationary solutions of the wave kinetic equation, and these are exact analogs of the Kolmogorov spectra in hydrodynamic turbulence. Okay, so these were discovered by Zakharov in the 60s and have been they're of great interest for physicists. So mathematically, there's very little work on that. So this is something that is, with still our understanding, could be improved in many, many ways here, despite some works by Escobar Velasquez and Sofra and Tran. So this is sort of beyond of what I will talk about today. Today we'll be mostly interested in sort of giving a rigorous derivation of this wave kinetic equation, or in other words, like giving you an analog of Lanford's theorem in the context of nonlinear waves. So in terms of the mathematical literature, the initial focus of the mathematical research was on constructing solutions that exhibit energy cascade. This is one of the conclusions, or this is one of the implications of the kinetic theory. One of those implications, it tells you basically that there are solutions of the nonlinear Schrödinger equation for which the energy moves its concentration zone from low frequencies to high frequencies. This is called an energy cascade, and it is precisely implied by those cascade spectra over here. Okay? So this was Bourgain's idea that rather than go through the kinetic equation and trying to see this energy cascade as solutions of the kinetic equation, let us instead look at deterministic solutions from of the PDE. So take a dynamical systems perspective and look at the growth of Sobolev norms of those solutions. Okay? So if the energy of the system moves from low frequencies to high frequencies, then this should be accompanied by a growth of those Sobolev norms, because those Sobolev norms penalize high frequencies more than they penalize low frequencies. Okay? So if the energy moves to high frequencies, then you will see it in terms of a growth of those norms. The most influential work here is work by Colliander, Kiel, Staffanata, Coca, and Tau, who showed that there exist solutions for the cubic analysis on TD that exhibit finite but arbitrarily large growth of Sobolev norms. So there are solutions that start, say, smaller than delta in HS, and then at a later time they become larger than, say, 1 over delta. Okay? However, those solutions are very special, and they are very far from generic. And whereas the theory sort of tells you that this behavior should be much more generic than that. So whether this behavior is generic or whether there exists solutions that exhibit infinite growth of Sobolev norm, these are all outstanding open problems on TD, despite some partial results in this direction. And there are some people in the audience who you can ask about that. Okay, so of course, again, a rigorous understanding of the kinetic approximation would give you another way or another insight into this question of energy cascade, because then you can look at the equation that is satisfied by the modulus of the Fourier modes, and this should give you a lot of insight. Okay, so let's get back to our question of interest today, which is, as we said, Hilbert's sixth problem in this nonlinear wave context. And then I will get to exactly to Simone's question, which is if you like, the order of the limits. How do I take the limits? So remember, when we took the Boltzmann limit, I told you that you don't just take the limit n goes to infinity and r goes to 0 arbitrarily. You take them in such a way such that n times r to the d minus 1 stays order of 1. Okay? This is something we will call scaling law. So scaling law tells you the relative rates of the limit L goes to infinity and alpha goes to 0. Okay? So, so a priori, you can start by considering all possible scaling laws. All possible ways L and alpha go to 0, L and alpha go to their limits. So, and this can be encapsulated in this compact formula that alpha is equal to alpha minus gamma, where gamma could be 0, could be infinity, but could be also anything in between. So if gamma is equal to 0, this corresponds to first taking the limit L goes to infinity while fixing alpha, and then taking alpha to 0. And this and vice versa for gamma equals to infinity. Or you can take them simultaneously in such a way such that alpha equals L to the minus gamma. Okay? And typically the choice of the scaling law will depend on the physical context that you're in. Okay? So one first thing that you notice in this business, I want to elaborate on it because of I don't have time, is that not all scaling laws are admissible. So you cannot take gamma between 0 and infinity and get a kinetic theory. Okay? Actually, this is the range of exponents gamma, or the range of scaling laws that are possible for you to get to the wave kinetic equation is limited. So if you don't want to impose any restriction on the shape of your spatial domain, which is the box, the periodic box, then the only admissible range is gamma between 0 and 1. Okay? For example, if you consider the square torus, then this is the only range of admissibility. This is really related to resonances. This is the thing that dictates it is how strong your resonances and your exact resonances are. So this links the theory to dynamical theories like normal forms, etc., which tell you what is the range in each case. However, if you impose genericity conditions on the torus, so if you assume you're working on a torus where the aspect ratios are not necessarily 1, but instead you assume that the aspect ratios are rationally independent in a generic way, so you impose Diophantine conditions, then this possible range of scaling laws widens a little bit, all the way to gamma between 0 and d over 2. Okay? These are really come from dynamical perspectives and some estimates. So I won't go into them today, but everything can be stated in terms of this diagram. So I can state the conjecture in terms of this diagram. So let me explain it. So the horizontal axis of this diagram is log alpha inverse over log L. Okay, so this is log plot of alpha versus the time. Okay, so once you fix log alpha inverse over log L, it means that you have fixed a scaling law. You have fixed how does alpha depend on L. Okay, so any point here on this axis dictates the scaling law. So you fix a point on the axis means that on the x-axis means that you have fixed the scaling law, and then the red line tells you. So the vertical axis is the time, again in a log plot, log t over log L. So this is the time for which you want to prove the approximation. Okay, the approximation that we talked about earlier, this central object over here. For what times can I prove that the NLS dynamics are approximated by the kinetic dynamics? Okay, and what do I want? I want to basically reach the time, the kinetic time, which is 1 over alpha squared. I want to show that the NLS dynamics is approximated by the kinetic dynamics up to times 1 over alpha squared. Okay, so this is the red line. This is the time interval. So you want, for each scaling law, you want to reach the red line in terms of the approximation between NLS and the kinetic equation. And as I said, so if you don't want to impose genericity conditions on your domain, then this is the region that you're interested in. This is only this segment is of interest. If you indeed want to impose genericity conditions on the torus, then you have access to this part of the red curve. Okay, so but I mean, for most of this talk, we'll be interested in the kind of theorems that we prove without imposing any genericity conditions on the torus. Okay. So here are some previous results on similar and close by questions. So there's a somewhat related work of Erdős, Selmhofer, and Yao from 2008 where they considered the linear Schrodinger equation with a random potential. And over there as well, there's a kinetic equation that you want to justify, and even more interesting things that happen after this kinetic time scale. Then there's also a work of Lucanen and Spohn in 2011 that studied the problem of time correlation. Basically, you want to prove the exponential decay of the time correlation of the equilibrium Gibbs measure in that setting. Okay. And then there are some partial results by various authors, Fau, Daimov, and Kuxin, Miyoki, Vladots, who studied stochastically forced equations, so an equation with additive force, and they had some partial results there. However, the first attempt at the full problem was in a work that we did a few years ago with Tristan Buckmaster, Pierre Germain, and Jalal Shatta. So let me explain all those results in terms of this log-log plot. Okay, so remember that the goal is to reach to the red line. Okay, you want to prove the approximation of the NLS dynamics with the kinetic dynamics all the way up to times that reach the red line. So in our very first work, we were still far from the red line, but we really set the problem up, and there's a part of this theory that relies on some number theoretic results. The advantage of this work is that it settled all the number theory that is needed in order to get those results. Then in 2019, there were simultaneous works essentially between two groups, one by Collot and Germain, and the other was myself and my collaborator Yu Deng. So in Collot and Germain, what they did is that they proved this approximation up to this yellow rectangle. So I should point out here is that this does not touch the red line. It stays epsilon far from the red line. So really we don't reach at that time, we did not reach the kinetic time. We call those subcritical timescales. So this corresponds to proving the approximation between the NLS dynamics and the kinetic equation up to times that are of the form L to the minus epsilon times the kinetic timescale, where epsilon is a positive but could be arbitrarily small number. Okay, so we call those subcritical timescales for reasons that I will explain later. And then, as I said, around the same time with Yudeng, we got to, we proved the approximation up to this blue line over here. So again, here we're not touching the red line, and this is the key point. But we're getting arbitrarily close to it at those 2 points. Okay, so we're still, this result is still a subcritical result, and which tells you that at this point, these are still very far from satisfactory results in the sense that we still do not get to the time scale at which the kinetic equation moves up to order of 1. Okay, so up to those time scales, L to the minus epsilon times the kinetic time scale, the kinetic equation moves, the change in the kinetic equation is order of L to the minus epsilon. We still write down non-trivial statements there, but you still do not get to the kinetic time scale because this is the time scale at which the kinetic equation moves order of 1. So this is what we call a full justification of the equation. So the full justification equation should reach times that are of the form delta times the kinetic time scale, where delta is an order of 1 parameter. Okay? This would be exactly like the theorem that Lanford's theorem that I stated to you for in the case of Boltzmann's equation. Okay? This would be the analog of that.
The delta here, sorry,
Yeah,
is bounded above by something, or you can
by 1.
by 1, and that's because Lanford, I think delta is less than 1.
Right, right. And here as well, it will be less than 1. But the key point is that it won't be dependent on the asymptotic parameters. It won't be dependent on L and alpha, which are going to 0. Okay? So this is the main theorem for today, in a way. So this is the result of a couple of joint works with Yudeng that we did last year in 2021, where we give a rigorous justification of the wave kinetic equation and the other things that I mentioned in the kinetic conjecture earlier on. So let's read through this slowly. So again, we remind you, considering NLS on a periodic box in dimensions d greater or equal to 3. I take n initial to be a non-negative Schwartz function. Again, this is an overkill. I don't need it to be Schwartz. It's just a finite amount of decay, and a finite amount of smoothness is more than enough. But let's not go into that here. And then I take the initial data for NLS to be well prepared. What does this mean? I remind you, this means that if I take the Fourier transform of the initial data, then this is given by square root of n initial at k, and then I randomize it by those eta k of omega, those IID random variables. And those IID random variables, the only thing that you need to assume on them is that their low is rotation symmetric and has exponential tails. Again, on a first reading, just think of them as being IID Gaussians. Okay? Then the third thing that I need to specify are the scaling laws that we discussed before. How does alpha go to 0 with respect to L? We, in this first paper, we took alpha going to 0 like L to the minus gamma, where gamma is like 1. Basically, it's not, it's in an interval around 1. Okay? So something like 1 minus a small thing up to 1. And recall that the kinetic time scale is 1 over alpha squared. Okay, there's a technical assumption when gamma is equal to 1 is that you need to assume genericity condition on the aspect ratio of the box. So gamma equals 1 corresponds to this point over here, which is really the threshold between theorems that work for any torus and theorems that for which you need genericity assumption in order to get them. Okay, that's why we have to impose genericity conditions when gamma equals 1. Those are not imposed when gamma is less than 1. We don't need them when gamma is less than 1. So then you have what you want. You have that there exists delta less than 1, which is fixed. It's a small parameter, but it is fixed. And an absolute constant nu, such that you have the following, that If you look at the variance of the Fourier modes of NLS at later times, then this is well approximated by the solution of the wave kinetic equation at the Van Hove time scale, so at times t over t kinetic, plus an error that goes to 0 as L goes to infinity. Okay? And the key point here is that this approximation holds uniformly up to times that are of the form 0 up to delta times the kinetic time scale. So you reach delta times the kinetic time scale, where delta is essentially an absolute constant. Okay? Okay, so this was our first paper on the subject. Soon after so this paper tells you the asymptotic of the second moments of the solution, or the variance of the solution, but you don't have to stop there. You can actually get information about the asymptotics of the higher moments of the solution, and even the distribution of the solution at later times. So what does this say? It says that suppose you have, you take R distinct wave numbers, K1 up to Kr, so R distinct Fourier modes. Then this is how you formulate the propagation of chaos hypothesis. That is, the right way to formulate it is in terms of studying the joint distribution of those Fourier modes. So what you have is that the random variables you had of t at those different frequencies or different wave numbers, those are initially independent. Okay, so what happens is that, as I said before, at the microscopic level they become dependent, or they develop correlations because of the nonlinear interaction, but in the kinetic limit, or at the macroscopic level, they retain their independence when you take the kinetic limit as goes to infinity. Okay, so again, this is I'm paraphrasing this this statement. Stating it precisely would require me to write down a math equation, but it's not a big deal. But I just want to emphasize that this is really at least to me, maybe it's not surprising to physicists, but to me it was a very deep. I felt it was a very deep and surprising statement. Although the whole theory relies on it, so in ways it wasn't surprising, but it's very, very deep. The second thing is that not only you can write down the asymptotics of the variance of the Fourier modes, but you can also essentially write down the asymptotics of the law of the Fourier mode. So you really can find the full distribution. And the law of the Fourier mode, u hat of tk, converges. I can write down its equation. So u hat of tk is a complex number, so it lives in R2. So if I'm looking at its law, so I push forward the probability measure, then the law is a function that lives on R2. So this function I denoted by rho k of tv, and this rho k of tv satisfies the following linear PDE. Okay, so there are parameters, two parameters in this linear PDE, sigma k and gamma k, which can be computed explicitly in terms of the solution of the wave kinetic equation. Okay? So you really can say everything about the higher order statistics of the solution as well in the kinetic limit. Okay, and finally, there's a corollary of this part 2, which is another surprising statement that was very well known or very well predicted by physicists, but again, to me, was a very surprising thing to happen, which is the following, that if you start with initial data that are Gaussian, so if you pick those eta k to be Gaussians, then, of course, all this will be completely messed up at the microscopic level, because at the microscopically, things, all those correlations will be destroyed. But at the macroscopic level, once you take the kinetic limit, this Gaussianity is retained, and the law of the Fourier modes u hat of tk is Gaussian, and its variance is given exactly by the solution of the wave kinetic equation. So this is something that's called propagation of Gaussianity. Okay. So I should mention that this, after we derived this equation for the law, we realized that it was actually written in the physics literature in those works, which was an interesting confirmation of those conjectures. Okay, so back to the log-log plot. What did we prove here? We proved that we can indeed get to the red line. Okay, so we get to the red line, and we prove this green segment of this red line. Okay, so this is what was presented to you on the previous 2 slides in terms of the log-log plot. So for scaling laws that are in this region, so this corresponds to alpha equals L to the -1 or L to the -0.9, for example, you get exactly to the kinetic time scale. You can really justify the approximation up to the kinetic time scale as you want it. Okay, and in preparation right now we are writing down we can extend this approximation for all the scaling laws, essentially all the scaling laws that are of interest on a square torus, or if you don't want to impose genericity conditions on your torus. Okay. Okay, so this field has witnessed indeed an explosion of activity in the past couple, or in the past few years, and particularly in the past couple of years. So there was shortly after our work, there was work of Staffelani and Tran, who considered a discrete KDV type equation. So it was a discrete equation, but instead of starting with random data and keeping the equation deterministic, which is what we do, instead they add a forcing term, a stochastic forcing term to their equation. So they deal with an equation that is a stochastic PDE, and this forcing term is chosen in a very careful and nice way, in the sense that the stochastic force, it's not an additive white noise force, but it's a force that essentially keeps randomizing the angles in time. Okay, so it's a Stratonovich type stochastic force. This was a model that was proposed by Fau a few years ago. And in that case, they also give a derivation of the wave kinetic equation at the kinetic time scale, similar to, you can state the result similar to our statement. And in the particular scaling law, alpha equals L to the 0 minus. So you take L goes to infinity first, and then you take alpha to 0. Then there was recently work by Ma, who considered the same equation, but without the stochastic forcing. He added dissipation instead, and he would get the approximation up to subcritical times, so times that are of the form L to the minus epsilon times the kinetic time scale. And then there were works of Dubach, Germain, Harrop Griffiths for a model of random distribution relation. And then there was some work on quadratic Schrodinger equation in an inhomogeneous setting. All of those results are for subcritical times. They do not reach the kinetic time scale, but they get to L to the minus epsilon times the kinetic time scale. And then also recently with Ricardo Grandi, we considered the equation with dissipation and additive forcing, stochastic forcing over here. And then over here, as also there's a kinetic equation that you can write. And over here also we got to the subcritical time, but I don't see any reason why one cannot redo the process that we did in the deterministic setting in order to get to the critical time. Except the only thing is that it's a lot of work. Okay, but I don't foresee any obstructions there. Okay, so let me skip this. I mean, just very quickly, the way for those of you who are familiar with the derivation of Boltzmann's equation or derivation of equations starting from first principles. Usually this happens, the Boltzmann equation appears as the first equation in a hierarchy of equations that's called Boltzmann equation. There's also a hierarchy here that's called wave kinetic hierarchy, which we can also give its rigorous derivation. Okay, so let me just, okay, so I only have a couple of minutes, so let me, in those 2 minutes, try to give you an overview of the proof. Okay, so the proof is based on a diagrammatic, those proofs are usually based on diagrammatic expansions, so you expand the solution in Feynman diagrams. So these are the Picard iterates, U0 up to Un plus a remainder, okay? And those remainders, each of those iterates is represented by a tree. So the nth iterate is represented by a ternary tree that has n branching nodes. I will show you a shape of the tree on the next slide. And each of those Un is a multilinear Gaussian expression, okay? And these are referred to as Feynman diagrams, okay? So this is, for example, this is an example of those trees. Look at just this part of the diagram over here, or the picture over here. This tree appears if you iterate 3 times in the third iterate of the solution. Okay, the 3 times because there are 3 branching nodes in this tree. This is called the scale of, we call the scale of the tree. Okay, now, but you're looking at the variance of the Fourier modes. So you are multiplying U and U bar, which means that you are taking a tree and multiplying it by its conjugate. Okay, what this means is that by using something that's sometimes called Wick's theorem or Isserles theorem, this corresponds to, in terms of the Feynman diagram, what you get is the following. You get two trees like those that are shown over here, but the leaves of those trees, so these are the leaves are the endpoint modes of those trees, are paired to each other. So this red leaf is paired to this red leaf, this yellow leaf is paired to this yellow leaf, and the green leaves are paired to this leaf, etc. So you have complete pairing of the leaves. And, and as a result, you have two main difficulties that you have to overcome. The first difficulty is factorial divergence, which is that there are factorial number of diagrams. Okay? And this is a problem if you're doing a power series expansion. If you have a power series sum of an t to the n, and if an grows factorially, then you're doomed, and you cannot prove that this series converges. The second difficulty, which is called probabilistic criticality, and this comes because if you look at the iterates of the solution, the n plus first iterate is only better than the nth iterate by a factor of delta, rather than a factor of L to the minus epsilon. So this is why I called times of the form L to the minus epsilon times the kinetic time scale subcritical times, because those, if you study the problem on those time scales, you get a gain of L to the minus epsilon every time you iterate more, if you go from the nth iterate to the n plus first iterate. But since we want to get to times that are order of delta times the kinetic time scale, the n plus first iterate is only better than the nth by a factor of delta, which is an order of one factor. Now this implies that the nth iterate, the best thing you can say for it is that it has size order of delta to the n. So if I want to show that, or if you want to consider that this nth iterate, capital N iterate, is an error, I need to go to n that is of the form log L over log delta inverse. So something that diverges with L. Okay? In other words, I need to expand my solution up to orders that diverge in the kinetic limit. Okay? So, let me maybe just finish with the strategy. That's what you want to do. What you want to do is that you want to classify your couples. So you have written the, you have written the variance of the Fourier modes as a sum of those diagrams. So these are pairs of trees that we call couples. And those couples, as we said, there are factorially many of them. So the idea is to classify those couples into groups. The first group, which has the worst case scenario estimates, so this is estimate has delta to the n, size delta to the n, you can classify it precisely, and the key point, the key feature of this first group is that there aren't factorially many of them, but there are exponentially many of them. And indeed, there will be exponentially many of them. And the second part of the strategy is to prove that the or the remaining factorially many couples, so they satisfy much better estimates than the worst case scenario. Okay? So, and in particular, they feature a gain of power of L that is sufficient to offset the factorial loss. Okay? So this is the strategy that you want to take. Okay, so if both those strategies turn out to be much harder to execute than one expects. So the first group turns out to have some things that one does not expect. But maybe I can just mention one little thing about the second group of couples, the ones that you expect them to have better estimates. So, so this is the content of rigidity theorem. The rigidity theorem, which is probably the most important theorem in this work, tells you that apart from those very precise couples that have maximal estimates, you get a big gain on your Feynman diagrams. So the way it's stated is the following: is that if you perform a type of surgery on an arbitrary couple, so you take a very big couple, an arbitrary big couple, the first step is remove out of it those structures that give you maximal estimates, which are identified in the previous slide that I skipped. But once you do that, you'll get a reduced couple, and the key point is that in this reduced couple, you'll get a gain of the form L to the minus R, where R is comparable to the size of this reduced couple. And this is precisely what you want to offset the factorial divergence. And to prove that, this is a really combinatorial problem. And the way we do it is that we translate this combinatorial problem. Instead of doing the counting on such couples, we do it on something that we construct that is called molecules, which is a better way, or the right way in many ways, to do this combinatorial problem. And so this molecule, this is a very small molecule, but it could be very, very large. And the way you think about it is that you want to put an algorithm in order to destroy this molecule, basically to destroy its bonds, and in order to, and which by the end of which you do the counting effectively. And we do that by writing down something similar to a computer program, and you prove that this program eventually ends and gives you the required estimates. Okay, so I'm out of time, so I'll stop here.